Okay, so far, everything we've done so far has been a pure acid or base or a salt. Okay, we had no source of conjugate base or conjugate acid coming from any other substance. Okay, so everything we've done has had initial 0 for hydronium, realizing that we're neglecting water, and 0 for acetate ion. But what happens now if I have some other source of that acetate ion coming from somewhere? Say I add some soluble salt, such as sodium acetate, to the solution. Okay, what effect will that have on this equilibrium? Well, if I have some acetate coming from another source from that soluble salt, then what's going to happen is it's going to shift that equilibrium to consume up that added acetate ion, which is going to make this equilibrium shift to the left. Now, if it shifts to the left, that means that I will consume up that hydronium ion. More hydronium ion will be consumed. Therefore, I will be decreasing hydronium ion, which also means then my pH then will increase, because the concentration of my hydronium ion affects my pH of my solution. This is what we refer to as the common ion effect. It is a shift in an ionic equilibrium caused by the addition of a solute that provides an ion common to that equilibrium. In this case, that common ion is that acetate ion, which is causing the equilibrium to shift. The pH of the acidic solution, of pure acetic acid, or pure acetic acid solution, is lower in pH than that of the acetic acid sodium acetate, okay, because of this common ion effect. Because I added that soluble salt to the solution, the pH will be greater than if I just had the pure acid itself. Alright, so what happens in the common ion effect is you have some common ion that's going to cause the equilibrium to shift. Okay, let's take for instance sodium acetate here. It breaks up to sodium ions and acetate ions. We have a source of acetate ions coming from that sodium acetate, that soluble salt. Okay, now how is that going to affect our calculations? In the past, what we've done is we said we had X amount of hydronium and X amount of acetate, okay, and did our calculation. But now we have some molarity, some numeric molarity of acetate ions coming from that soluble salt. We're going to have to account for that in our calculation, which means I'm also going to have to put that with my X amount of acetate, some number of molarity of acetate. So I'm going to put that in my calculation because that's going to shift my equilibrium to the left. Okay, it's going to cause my equilibrium to shift to the left, which is also going to cause my concentration of hydronium to go down, which then will affect my pH and cause it to go up. Okay, be a higher pH. So by adding that soluble basic salt, my pH is going up. It's going up in pH. To increase. The equilibrium composition will shift to the left, and that degree of ionization of acetic acid is now decreased, meaning I'm going to form less hydronium ions. Therefore, I will have a higher pH compared to that pure acid. The repression of the ionization of the acetic acid by sodium acetate is what we refer to as an example of a common ion effect. There's another source of ion coming from an additional solute added to the solution. Okay, hence common ion. Now, when we're talking about acids and bases, we have a special name for the common ion effect, which is called buffer, which we'll talk about later on in this lesson. One of the coincidences of having a common ion is that the pH will change. Okay, if I have an acid and I add a soluble basic salt to it, the pH is going to get higher. The opposite effect, if I have a base and add a soluble acidic salt, the pH is going to go low. When common ion effects involve weak acids and conjugate bases, or vice versa, meaning a weak base and a conjugate acid, it is referred to as a buffer. A buffer is a solution characterized by the ability to resist changes in pH when limited amounts of acid and base are added to it. If I had a pure acid or pure base and I add acid or base to it, the pH is going to dramatically change, going up or down depending on what the situation is. However, if I have a buffer solution, I have acidic and basic components in that buffer, which can absorb that additional acid or base and basically keep the pH relatively constant. I'll show you this in a calculation later on in later on in the presentation. Buffers contain either a weak acid and its conjugate base or a weak base and its conjugate acid. Typically, the conjugate is in form of some salt. Remember, when we're talking about conjugate species, we're talking about species that differ by one proton. Okay, so when we're trying to decide if this is a buffer system, they should differ by one proton between the conjugate species. We've got a weak acid and a conjugate base differ by proton, or a weak base and its conjugate acid, they also differ by proton. The other important thing about a buffer that we should realize is that we're talking about weak species. Okay, we can't have a strong acid or a strong base in its conjugate base and call it a buffer, because that conjugate base really isn't a conjugate base. Okay, as we spoke about before. Okay, it doesn't really want to go under the hydrolysis and accept that proton. Okay, so it has to be a weak species, and we differ by one proton. Let's look at acetic acid and sodium acetate. Is that a buffer system? Well, I have a weak acid. Okay, I have my weak acid, and I have its conjugate base. That is a buffer. Remember, if you write your equilibrium of your acetic acid, what we're looking for is the reaction with water and its conjugate base, which if we write the reaction, you got your conjugate, the Bronsted-Lowry, the acid's going to donate the proton to the water, which then gives me C2H3O2 minus. So we're looking for that acid and its conjugate base. Okay, and that's what we're seeing here. We got our acid and our conjugate base species, because that salt, it's a soluble salt, it's going to break up into sodium ions and acetate ions. Okay, giving me my acetate ions, and I have my acid component. What about hydrogen cyanide and sodium cyanide? Is that a buffer? Well, it has an acid, it's a weak one, and it has its conjugate base. Yes, that's a buffer. What about carbonic acid and potassium bicarbonate? Well, it's a weak species, and it has a conjugate base, HCO3 minus, that differs by one proton. So yes, that's a buffer. It has a weak species, and it has the conjugate base, which differs by one proton. H2CO3, HCO3 minus, that's a conjugate acid-base pair. So yes, that's a buffer. What about ammonia chloride and ammonia? Well, the molecular species in this case is the ammonia, but we're still talking about a weak base, and we're still talking about a conjugate acid, different by one proton. So we have our ammonia ion, because ammonia chloride will break up into NH4 plus CO minus, okay, and your ammonia. Okay, so we're talking about a conjugate acid-base pair, except we got a molecular species of the base, and our conjugate acid is the ammonia ion. What about H3PO4, phosphoric acid, and sodium biphosphate? Is that a buffer? It's a weak acid, but the problem is it's not a conjugate acid-base pair. We got 3 protons versus 1 proton. Okay, so we're different by 2 protons. The conjugate base of phosphoric acid is H2PO4 minus. Okay, so in this essence, this is not a buffer. Differs by 2 protons. That does not meet the conditions of a buffer. What about HCl and sodium chloride? Well, we're talking about HCl and Cl minus. That differs by a proton, so it looks like a conjugate acid-base pair, but we're talking about a strong acid. So that Cl minus is not really a conjugate base. Okay, it's not going to undergo any appreciable hydrolysis. So by definition of a buffer, that 8Cl sodium cyanide, sodium chloride is not a buffer. So the answer is no. It's a strong acid, so it's not a buffer. Thus, a buffer contains both an acid species and a base species, okay, in an equilibrium which allows it to absorb any added acid or base and keep the pH of the solution relatively constant. So how a buffer works is if I add any acid, okay, and say I got a acetic acid, I have acetic acid and a sodium acetate buffer. Okay, if I add acid to it, it's going to want to neutralize with the base component. So basically that acid will react with that sodium acetate, consume up all that acid, and basically keep the pH relatively the same. If I add base to it, it's going to want to react with the acid component, and basically that acid component will consume up all that base and keep the pH relatively the same. So we have both components there to absorb any additional acid or base that keeps that pH relatively the same. And when we say relatively the same, we're talking about changing, 0.05, 0.1 units, very small increments. Contrary to if I had a pure acid or pure base, the pH will change dramatically. And I'll show you this in a calculation, how that pH doesn't change very much. Let's consider a buffer with equal amounts of HA and conjugate base A minus. We're taking a generic salt, sodium A, okay? It's a soluble salt, so it breaks up into ions, sodium plus and A minus. And we have our weak acid, which undergoes hydrolysis to form hydronium and A minus. For a buffer to be truly a buffer, you need things that has equal amounts of molar concentrations of your acid and your conjugate base. Now, when I say equal molar, it doesn't have to be exactly the same. There should be similar numbers close to, within a power of 10 difference, okay? So you should have things like 0.51 versus 0.25 type thing, okay? They got to be similar concentrations. They can't be off by factors of 10. As long as you get similar concentrations, then you have a buffer system along with the weak species with its conjugate component. Let's take this particular reaction now. And let's say I add a small amount of acid. Okay, if I add a small amount of acid, it's either going to react with the HA or the A minus. Those are my two components. Okay, so will it react with the acid or the base component? Well, if I add an acid, it wants to do neutralization, so it's going to want to go after a base component. So in this case, since it wants to go with a base component, adding any additional acid, it's going to react with the A minus. So let's write that neutralization reaction. So I'll take my A minus plus that acid, okay, which we'll write as hydronium ion, okay, will form now H2O, water, and HA. Basically, you just have in your conjugate acid base, you got your proton being donated to A minus to form your products. Now, I'm adding a small amount of hydronium ion, acid, to this. Okay, so in the process, I'm going to have more A minus than I have acid that I'm adding. So what's going to happen is that H3O plus, that acid, is going to be consumed. And in the same time, that A minus concentration, since it's being reacted, is going to decrease. So what happens when I add that acid component is the amount of A minus will decrease, and all that hydronium ion that I added with that acid will be consumed up. Since this is a neutralization, it's going to form some products. It's going to form water and HA. Well, what's happening to the concentration of HA in this process? It's going up. I'm forming some HA. Now, how will this affect my equilibrium above? Okay, well, if I have more HA being formed, so I'm having some HA being formed, and I have A minus being consumed, okay, which way is this equilibrium going to have to shift to counteract that additional HA and that reduction of A minus? It's going to have to shift to the right, okay? It's going to shift to the right to consume up that additional HA and produce more A minus. In that process of doing that, it replaces that consumed A minus and at the same time maintains that pH to relatively the same amount. Now you may say, well, wait a minute, if it's shifting to the right, I'm also producing some hydronium ion. That should change the pH. But you got to remember, we already have a concentration of hydronium. All we're doing is doing this shift and we're forming that X amount when we do our calculation. Well, how big is that X compared to the species that we're adding them to typically? A small amount. So that X is a very small number compared to what we had in hydronium to begin with. So it will change because I'm adding more hydronium, so the pH will go down, but only by a small amount. There'll be a small decrease in pH due to that additional hydronium, but not a large dramatic change because it's a buffer system. If it wasn't a buffer, it would be a dramatic change, and I will show you that in a calculation later. Now what happens if I add a base component? Okay, what if I add any base to this? Okay, what if I add any base to this reaction? Which component is it going to react with? Well, since I'm adding base, it's going to react with the acid component, which means it's going to react with HA. Now, in a similar process, okay, what's going to happen is that amount of base that I add will be consumed up. My concentration of HA is going to go down. And on the other side of the products, okay, you'd be forming some A minus on the other side. So that's going to be increasing. Okay, so you have HA decreasing and A minus increasing. So which way is this equilibrium going to shift in? After I reach equilibrium, I'm decreasing HA and I'm producing more A minus. It's going to shift to the left to try to produce more H minus, HA and consume that additional A minus, which then what happens to the concentration of your hydronium then? It will be going down. But once again, be going down by a very small amount, that X amount. Okay? So what happens here is I'll replace that consumed HA and maintain the pH. There'll be a slight increase in pH because of that decrease in hydronium, but that's a slight amount. Okay? Remember, that's a small amount compared to what I had before, keeping the pH relatively the same. Alright, let's see if we can calculate the pH of this particular problem. An aqueous solution is 0.25 molarity in formic acid, and that's HCHO2, and 0.18 molarity in sodium formate, NaCHO2. What is the pH of the solution? The Ka of formic acid is 1.7 times 10 to the negative fourth. Okay, we said that what we're going to do anytime we're trying to calculate pH, we're going to ask a particular question first, which is it a single solute or is it a reaction? Well, looking at this particular problem, since I have two components, it's not a single solute, so it looks like a reaction. So when it becomes a reaction, there's the next question that I want you to ask yourself. Is it a neutralization or is it a buffer? Okay, so you need to know, is it a neutralization reaction or a buffer? Well, naturally, we haven't covered neutralization yet, so it's probably a buffer, but let's see if we can determine that it is a buffer. What we would do is look at it and you say, okay, I have this acid, which is HCHO2, and I have this soluble salt, which is sodium formate. It has CHO2 as part of that component. So I'm looking at HCHO2 and CHO2 minus, since it's a soluble salt, it breaks up. What does that look like? Well, it's a weak species and it has its conjugate base. That's a buffer. So we have a buffer system. Okay. Now, what if you didn't look at that and you couldn't determine that that was a buffer? Then you would have treated it as a neutralization. Well, let's see what happens when you write that as a neutralization. You would have HCHO2 plus NaCHO2. Let's see, what are my products? Well, the cation's going to exchange, which will give me NaCHO2 plus HCHO2. Now, what do you notice about this reaction? Your reactants are exactly the same as your products. Your reactants equal products. Anytime you see that, that's an indication that you're looking at a common ion problem. Okay, which then you look at the common ions and you say, oh, this is an acid-base reaction, so this is a buffer. and then you know you got to treat it like a buffer. Now, what if you still didn't see it after you looked at it and you decided, okay, I'm going to go on with it as a neutralization reaction? Well, as long as you keep your components together and you follow your concentrations, because you go through it and you're going to eventually come up with some concentration of sodium formate, and you come up with some concentration of sodium formate on this side as well, some value. As long as eventually you see they're the same and you treat them as one, you can still get the same answer. So if you follow the process that I tell you, and you don't make any mistakes, okay, you can still get to the right pH, treating it as neutralization. It's not a good idea to do it that way. It's better to just look at it and say, oh, that's a buffer, and handle it as a buffer. But if you follow the system I'm showing you, you still can get to the right answer if you look at components and you say that this is the same component as this, I just got to add those up and go on with it. You can still get the right answer. However, as I said, easiest thing is look at the components and say, oh, I got a weak acid and I got a conjugate base. That's a buffer. Anytime I'm dealing with a buffer, my next step is to write the dissociation of the soluble salt. Okay, I want to do that because I want to remind me I got to use that number as I did in the past. Okay, so I write my soluble salt. I got my sodium formate, gives me sodium ions and formate ions. My concentration is 0.18 for both components. That's because I got 0.18 of sodium formate and everything's 1:1. If I had a 2 in front of that formate ion, then I would have to double the concentration. Once I do my dissociation, then what I do is I do my hydrolysis of the acid component, which would be HCHO2, gives me hydronium and my formate ions. Then anytime I write an equilibrium, then it's always the next step is my ice table. I set up my ice table. I got my initial, which is the 0.25 of my formic acid. Okay, I have 0 for my hydronium. I do have the water, but we're neglecting it. But this is why I write the soluble salt on top. I want to remind myself that I have to put in that 0.18. It's not 0 anymore. Remember in the past it's been 0. It's not 0 anymore. I got to remind myself to put that in because that's going to shift my equilibrium. I got to account for that. So that's why I write the soluble salt on top. Then I have my change. Well, it's going to have to go to the right because I have 0 hydronium, so it's always going to go in the direction that I have a 0. So that means I have minuses on my change on my reactant side and pluses on my product side. I need some relationship between them. So I'm going to go with X, X, and X. That's something we've been doing over and over with this acid-base stuff. Then I add them up to figure out equilibrium, which will give me 0.25 minus X, X, 0.18 plus X. Next question we ask ourselves is how are these related? How is 0.25 minus X, X, and 0.18 plus X related? And the way that we set up this problem, they're related through Ka. Now, could I have done this problem differently? Could I have written this as CHO2 minus plus water gives me hydroxide ions plus my conjugate acid? Yes, I could have worked it that way. The differences would be is that this would be a Kb problem, okay? And then when I solve for X, X is going to equal the concentration of hydroxide ions, okay? Could do it either way. Now, I preferably like to go with whatever the molecular species is in the buffer, okay? In this case, I got a molecular acid, so I'll continue on as a molecular problem. That way I don't have to flip between the Ka and Kb. So then I set up my Ka expression, which would be my hydronium ion concentration times my formate ion divided by my formic acid. Plug in my values, okay? X for hydronium, 0.18 plus X for my formate ion, and 0.25 minus X for my formic acid. Is equal to my Ka, which is 1.7 times 10 to the negative 4th. Now, I have some arithmetic to do here, or I can avoid the arithmetic. Okay, what we're going to do is basically if we know that this is a buffer system, okay, and we know that we got similar concentrations, meaning similar to within 1 power of 10 difference, then we can get rid of the plus X minus X. Okay, so if it's a buffer, we know it's a buffer. Okay, I know it's a buffer, and I have similar concentrations, then I will neglect X. Similar concentrations meaning within 1 power of 10 difference. Okay, so as long as I'm talking about close to the same power of 10, then I know I can get rid of it and move on. So now that will lead me to X times 0.18 divided by 0.25 equal to 1.7 times 10 to the -4th. Mathematically, I will multiply both sides by 0.25 and divide by both sides by 0.18. Which gets me X is equal to 0.25 times 1.7 times 10 to the -4th divided by 0.18, which is equal to 2.4 times 10 to the -4th molarity. This is where I'm going to ask myself another important question. The way that we wrote this problem, what does X equal? And the way that we wrote this problem, X is equal to hydronium ion. Okay, so it's equal to hydronium ion. If I wrote this as a base problem, then X would be hydroxide. Important question to make sure we don't make a careless mistake. Do our calculation of pH with negative log of my hydronium ion, which is negative log of 2.4 times 10 to the -4th, which gets me 3.63 as my pH. Now, if we want to ask ourselves, does this answer 3.63 make sense? Well, since this is a buffer, that means I have acid component as well as base component. So to be able to determine where the pH should be for that buffer, I'm going to have to look at the Ka and Kb of the acid and conjugate base. In this case, the Ka is 1.7 times 10 to the -4th. If I divide it into my Kw, that would give me a Kb of 5.9 times 10 to the -11th for my conjugate base, my formate ion, which means since I have a larger Ka than Kb, it is a better acid, therefore it will have an acid pH. Okay, as long as my Ka is greater than 10 to the -7th, then I know I'm going to have an acid. Now, if we were to look at the pure acid, formic acid, 0.25 molarity, and you can calculate that just like we did in the past, you get a pH of 2.18. The buffering system, the 0.25 molarity of your formic acid and 0.18 molarity of sodium formate, gets a pH of 3.63. Notice that the pH is higher. It's larger because of the fact that we got that basic salt we had. But more importantly than that is, if I was to add any additional acid or base to that pure acid, okay, if I add any additional acid or base to that pure acid, the pH is going to change dramatically, go up or down depending on if I'm adding acid or base. While if I add it to this buffer system, the pH is not going to change a lot. It's going to stay around 3.63. I add some acid, it probably dropped to 3.57. Add some base, probably drop, 3.69, something like that. Going to basically stay similar to the pH, which is an important component, an important factor about buffers. Here's another example. Okay, a solution is prepared by mixing 0.15 molarity of acetic acid and 0.2 molarity of sodium acetate. What is the pH of this solution at 25 degrees C? And I give you the Ka of the acetic acid. Once again, we're going to look at this and ask ourselves, is it a single solute or a reaction? Well, it appears to be a reaction. Since it's a reaction, now I ask myself, is it a neutralization or is it a buffer? Well, if you look at this, I have acetic acid and I have the acetate ion coming from that soluble salt. That's a buffer. Now, if I didn't notice that and I did a reaction, what would happen? My reactants would be the same as the products, okay? Which tells me it's a common ion problem, and I look at it a little bit harder, I see, oh, that's a buffer. Okay, so we say this is a buffer. What do we do if it's a buffer? Well, the first thing, I'm going to break up that soluble salt. So I get my sodium acetate, which gets me sodium ions and acetate ions, which is in this case 0.2 molarity of sodium acetate, which means 0.2 molarity for sodium and 0.2 molarity for my acetate ion. What's next? Then I'll do my hydrolysis of my acid, which is my acetic acid gives me hydronium ions and acetate ions. Wrote in equilibrium, that means now I'm going to do my ice table. Write my initial for my acetic acid, which is 0.15. I have 0 for my hydronium, I'm neglecting the water. And then I wrote this soluble salt up here to remind me to put it in there for my initial concentration of my conjugate base. This reaction has to go to the right. Therefore, I have minus for my reactants and pluses for my products for my change. I need some relationship, which I will call X, X, and X. And then I add them up. So at equilibrium, I know I got 0.15 minus X for my acetic acid, X for my hydronium, and 0.20 plus X for my acetate. Next important question, how are those related by the way that we're setting this up? In this problem, it's set up as a Ka. So I get Ka is equal to my concentration of hydronium times my concentration of my acetate divided by my concentration of my acetic acid. Plug in my values, X for hydronium, 0.2 plus X for my acetate, and 0.15 minus X for my acetic acid. Then I know it's a buffer, and I have similar concentrations of my conjugate base and acid, so therefore I will neglect my X's, which then leaves me X times 0.2 divided by 0.15 equal to 1.8 times 10 to the negative fifth. Multiply through by 0.15, divide by my 0.2, which gets me 0.15 times 1.8 times 10 to the negative fifth divided by 0.2, which gets me 1.35 times 10 to the negative fifth molarity, where that red number 3 is my sig fig location. I have a guard digit that I left in my calculation. Next question. What does X represent in the problem that we've written? That X would be hydronium ion. So then I can calculate pH. It's equal to the negative log of hydronium, which is equal to the negative log of 1.35 times 10 to the negative fifth, which is equal to 4.87. Let's compare that to the pure acid. If I did 0.15 molarity of acetic acid by itself and calculated it, I would get 2.78. And you can see by our buffer system we have 4.87. So adding that basic salt increased the pH by about 2 units. But the important thing about a buffer, though, is if I added additional acid or base to that pure acetic acid, that pH is going to change dramatically. If I add it to that buffer system, that pH is going to stay relative the same, somewhere around 4.87. And this is where I'm going to take this particular buffer. I'm going to take this buffer right here, and we're going to add acid to it and show you that the pH doesn't change that much. So we're going to take 75 mils of that buffer solution we just calculated at 0.15 molarity of acetic acid and 0.2 molarity of sodium acetate, which had a pH of 4.87. So I'm taking 75 mils of that buffer, and I'm going to add 9.5 mils of 0.1 molarity HCl to it. Okay, and then we're going to calculate the pH of that. Now, this particular problem is only trying to show you that the pH doesn't change a lot. However, this is the same type of system that we're going to use when we're dealing with neutralization reactions. So it's important in the sense of this is laying the groundwork for how we do neutralization reactions. It's not a calculation I'm going to ask you to do trying to figure out the change in pH, but it is the same type calculation when we get to reactions of acids and bases. Okay, so it's a 4-step process. The first step is we're going to calculate the millimoles initially of all the components. That goes back to the first day of class when we talked about dealing with millimoles. Okay, I said I'm going to deal with millimoles, and this is where it's going to happen. Okay, in this type of calculation. Anytime I want to get millimoles, is just going to take molarity times volume. Okay, now to give me millimoles. Next thing would be writing the neutralization reaction. Okay, what is actually happening, neutralizing, and figure out how much do I have of each component left. Third step, new concentration of every species. Okay, that I believe is affecting pH. If it's not affecting pH, I'm not going to worry about it. And the last step is the hydrolysis. That's what we've been doing all along. So what we're going to do is add 3 new steps above what we've been doing. So when we get to step 4, we already did this several times. Okay, but the first 3 steps we're going to have to use to be able to get to that point. Okay, so the first step is we're going to have to figure out the initial millimoles of each component. We said we're going to do that by taking the volume and molarity. So if I want to figure out the millimoles of acetic acid, I'll take that molarity of acetic acid, multiply by the total volume of acetic acid. Remember, it's a buffer solution containing those components in it. And that'll give me my millimoles of acetic acid. Sodium acetate. I'll take my molarity of that sodium acetate and the volume of the sodium acetate, and that'll give me my millimoles as well. And then last, I'll take my molarity of my acid times the volume of that acid, and that'll give me my millimoles. So, for the millimoles of acetic acid, that comes to 75 milliliters times 0.15 molarity. Notice, remember I told you before, that milli is just a prefix, so we're just carrying that over, and we canceled out the liters. Okay, give me a millimoles, which is 11.25. The red number is my sig fig. I'm carrying 2 guard digits in this particular problem. Millimoles of sodium acetate, I have 75 mils times that 0.2 molarity, gives me 15 millimoles. And my millimoles of HCl is 9.5 times 0.1, which gets me 0.95 millimoles. Next step is neutralization. I'm going to figure out which components are going to neutralize each other. Well, I have my buffer in system. Okay, I already have my buffer. And then I'm going to add some HCl to it. So my HCl is going to react with one of those 2 components. In a neutralization reaction, my acid is going to react with a base. Okay, and that's what's happening. Okay, so basically I have opposites. So since I'm adding HCl to this, which component is it going to react with? Is it going to react with the acetic acid, or is it going to react with the sodium acetate, which is a basic salt? Since I'm adding an acid, it's going to react with the basic salt. So I'll write my neutralization, sodium acetate plus HCl. So basically to write my reaction, my sodium cation is going to come over and displace my hydrogen. Okay. So in essence, my products will be acetic acid and sodium chloride. Now I write a table. It's not an ICE table, but it's a change in millimoles table. So I'll write my table. I got millimoles to start with. We calculated 15 millimoles of sodium acetate. We calculated 0.95 millimoles of HCl. And we calculated 11.25 millimoles of acetic acid. And since sodium chloride is nowhere in the problem to start with, we have 0 of that. That's a product that's being formed from this neutralization. Now I got to do my change in millimoles. Well, you may recall back in General Chem 1, we did stoichiometry and we did figure out which was the limiting reagent, and that dictated how much product could be formed. Okay. Well, since in this case, in all your acid-based stuff, we always do it 1 proton at a time, what's going to happen is you get a 1-to-1 mole ratio. Well, since it's 1-to-1, what's going to be the smaller number is going to be my limiting reagent, and it's going to be my change in millimoles. So in this problem, my actual change is going to be 0.95 millimoles. Okay, all that HCl is going to be consumed, and I'm going to have an excess of my sodium acetate. So my change in millimoles then will be, for my reactant side, minus 0.95 for my sodium acetate and minus 0.95 for HCl. On the product side, we're forming that, so it's going to be a case of mole to mole, 1-to-1 as well. So I'll be increasing by 0.95 for my acetic acid and 0.95 for my sodium chloride. Add those numbers up, and what I find is I have 14.05 millimoles of sodium acetate, 0 HCl, 12.12 acetic acid, and 0.95 for sodium chloride. These are the numbers that I have to look at now to see pH. I've already done the neutralization. Now pH is going to come from the hydrolysis of this stuff. So I need to look at each component and see if they can affect the pH. Okay. So it gives me to step 3. I want to find the new concentrations for the species, but only those that affect in pH. So let's look at each component and see what we're talking about. Sodium acetate. What is sodium acetate? Is it an acid, is it a base, or is it a salt? It's a salt. What kind of salt? It's a basic salt. Okay, I got HCl. What is that? That's a strong acid. But we have 0 amount of it, so it can't affect the pH, so that's not something I got to worry about because I have 0 of it, so I don't have to worry about it. What about acetic acid? Well, naturally it's an acid. Strong or weak? Weak. Okay. Sodium chloride, what is that? Salt, acid, or base? Salt. What kind of salt? Neutral salt. What I want to do now is look at this basic salt, this weak acid, and neutral salt, and determine which one of those, if any or both, or all of them, whatever, is affecting the pH of the solution. Can a basic salt affect the pH of a solution? Yes. Okay, it's adding basicity to it, so that's something I got to worry about for the pH of a solution. Can a weak acid affect the pH of a solution? Yes. Can I add acidity to the solution? Can a neutral salt affect the pH of a solution? No, it's neutral. So therefore, we're looking at a case of I got to worry about the basic salt and I got to worry about the weak acid. I don't have to worry about the neutral salt. Okay, so I'm not even going to worry about that. So at this point, now I got to look at these two components left and say, do I have a neutralization? What's going on between these two components when I'm dealing with to calculate the pH? Well, we're looking at sodium acetate and acetic acid. Okay, what are we looking at again? Oh, a buffer. Okay, so how do we handle a buffer? Well, we do our concentrations. We break them up into our dissociation of a soluble salt, do hydrolysis of the acid, and do the calculation. So, next step now is then let's figure out the new concentrations of these species. I know I got 14.05 millimoles of sodium acetate and 12.20 millimoles of acetic acid, but I want concentration. So I got to take those millimoles and put it over the total volume, which in this case is, what's the total volume? 75 mils of the buffer plus 9.5 mils of that added acid. So step 3, new concentration for the species affecting pH, meaning I'm not going to worry about sodium chloride. So after neutralization, my sodium acetate amount millimoles is 14.05. I divide that by my total volume, which is 75 plus 9.5. You can see my prefix millis cancel, leave me moles per liter, which is 0.166 molarity of sodium acetate after neutralization. Do the same thing for acetic acid. 12.20 divided by total volume, 84.5, gives me 0.144 molarity of acetic acid. Right now, we're at the point of where we were when we did those last two examples. If I rewrote this problem and now said, I want to calculate the pH of this buffering system, and I have a sodium acetate solution of 0.166 molarity and acetic acid solution of 0.144 molarity, how would you do it? Same way we did before. You do your soluble salt, do your hydrolysis, and do your ice table, etc. Okay, so we had to do the first 3 steps to get to where we were in those other 2 problems we just worked previously. So next step is hydrolysis. Okay, just like we have just started this problem over, starting with 0.166 molarity of sodium acetate and 0.144 molarity of acetic acid, we do next would be our soluble salt. Break it up into ions, which gives me sodium of 0.166, which I don't really care about in this problem, and acetate, which is 0.166. Do my acid, which my acetic acid gives me hydronium ions and acetate ions. Do my ice table. Okay, put in my initial concentration. Remember, my initial concentration is now my new concentrations. Remember, we had the neutralization, so the concentrations has changed. Okay, so I need to put in my initial of what I calculated, which is 0.144 molarity for my acetic acid, 0 for my hydronium, and once again, I got to account for that conjugate base, which is 0.166, which I calculated again after the neutralization. Has to go to the right, which means I got minus and pluses on the product side, XX relationship. Equilibrium then is 0.14 minus X, hydronium is X, acetate is 0.166 plus X. Next question. How are these related through the way we wrote this? We wrote this as an acid hydrolysis, therefore it's a Ka. So I got my hydronium ion times my acetate divided by my acetic acid, which gives me X for hydronium, 0.166 plus X for my acetic acid, and 0.144 minus X for my acetic acid. Okay. Once again, this is a buffer. Okay, it's a buffer, and we have similar concentrations within the power of 10. Therefore, I can simplify my math and get rid of my plus X's and minus X's, which then gives me X times 0.166 divided by 0.144 equal to 1.8 times 10 to the negative 5th. mathematically, I'll multiply both sides by 0.144. I'll divide both sides by 0.166, which gets me 0.144 times 1.8 times 10 to the negative fifth, divided by 0.166, which gets me 1.56 times 10 to the negative fifth molarity, where my sig fig is that 1.5, okay, the times 10 to the negative fifth. What do we do here? Okay, I want to know, what does X represent in this problem? In this problem, X represents hydronium ion. Okay, that's important. Make sure that you know what X is representing. If this was a base problem, it'd be hydroxide. Which gives me pH is equal to the negative log of hydronium ion, which gives me negative log of 1.56 times 10 to the negative fifth, which gets me a pH of 4.81. Since the molecular species is an acid, I would expect my pH to be on the acidic side. Now, the ultimate goal of this problem was for us to determine how much the pH changed. But before I get to that, I wanted to bring up a point. A lot of times in books, instead of doing this on a concentration base, they will do it on a millimole base, okay, as a mole base. And that works, and the reason that works is if you look at the math here, once I get rid of the plus X minus X, this is moles per liter, and this is moles per liter, okay? Well, this liter is your total volume, okay? It's in the denominator of that numerator and the denominator of the denominator. What happens then mathematically is your total volume cancels, okay? Which allows just mathematically to do millimoles over millimoles and still get the same answer, okay, right? The ratio will be the same. That only works when you're talking about a buffer. Okay, if it's a buffer calculation, that works. I strongly suggest you don't do that. Go ahead and calculate your new concentration. Do step 3 and do a new concentration every time. Okay, that 10 seconds is going to save you some careless errors later. Okay, you can only do that if it's a buffer. If it's not a buffer, you can't do by moles. You got to do it by concentration. Look at the formula. It's in concentration. It has brackets. That means concentration. These have to be molarity. Okay, as I said, it will work on buffer because of the way the math works. That total volume cancels out. I suggest do it the same way every time. Follow the system I'm telling you, and you get to the correct answer. Your goal is the correct answer, not the shortest and easiest way to get there. Okay, you want the correct answer. That way you can get the points on the test. So do it the system that I'm showing you, and then you can get to that point and get the correct answer. All right, getting to our ultimate goal in this problem, which was the change in pH. The pH of this buffer system after I added the acid is 4.81. Let's compare that to the original buffer pH. So what was the change in pH due to that additional HCl? Okay, you have your final pH, which is 4.81. And you have your initial pH, which is 4.87. So if I do the change in pH, you can see it went down by 0.06 units. It went a negative 0.06. Since I added an acid, I expected to go down on the acidity side. Okay, and it did by 0.06. That's not a huge change. That's not a lot of change. That's a very small amount. Okay, now I want to show you that adding that same amount of acid to pure water would make a dramatic change. Okay, so I want you to realize that that is a substantial amount of acid we add, and the pH didn't change much. So let's look at this same problem, but deal with it as just pure water. Okay, so I'm going to take this same 9.5 milliliters of 0.1 molarity HCl, that same amount, added to the same quantity of solution, 75 mils, but this time it's pure water. It's not a buffer. As I said, I want to show you this to show you that the pH dramatically changes. Alright, so if I'm talking about the pH of a solution and all I have is HCl and water, then I need to figure out what is the actual concentration of HCl, and then from there figure out my hydronium and pH. Since I have 9.5 mils of 0.1 molarity and I'm adding 75 mils of water, I'm diluting it. So in essence, we're coming in on step 3 of the previous slide. We're coming where we got to figure out the new concentration. So let's figure out new concentration, because there's no neutralization, there's no concentration to figure out millimoles. All we got to do is figure out the new concentration, which would be my milliliters of HCl, 9.5, times my molarity, which is 0.1, divided by the total volume. basically doing your CV equals CV, figuring out your new concentration, which in this case is 0.0112 molarity. So now my question basically is, I have this 0.0112 molarity of HCl. What is the pH? Well, it's an acid base of salt. It's an acid. Strong or weak? Strong. How do we handle a strong acid? Ionize it 100%, which means HCl breaks up into H plus and Cl minus, which means I got 0.0112 molarity H plus and 0.0112 molarity of Cl minus. Don't really care about the Cl minus, but the H plus will give me my pH. Take my negative log of hydronium, which gives me a negative log of 0.0112, which gets me 1.95. Let's see how that pH changed. We know that pure water is a pH of 7. So you got 1.95 as my pH final. My initial was 7 pH. The difference is a negative 5.05. That same amount of acid changed the pH of that pure water to 1.95 pH units. So basically that buffer holds the pH relatively constant. It only changed by 0.06 units. Okay, so when I add small amounts of acid to base, that pH will relatively stay the same in a buffer solution. But that pH dramatically changed when I added to a system that was not a buffer. Homework 36 gives you questions about buffers. Okay, I give you questions about buffers, and it's more of a calculation of buffers, okay, like we did with the previous problems. I don't have anywhere I'm calculating the pH change, okay. However, this information is important to you because this is the same 4-step procedure we're going to use when we're talking about neutralization, which is at the end of this chapter, okay. So this is an important concept. It's just not something we're looking at on homework set 36. We'll look at it on other homework sets later on.